welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 11 in the series on section 2.6, Logarithmic and Exponential Equations. To begin, we must keep in mind that logarithms of a certain base cancel exponentiation of that base. And in the same way, raising a power to a log base that power of x will just give me x. That is to say, logarithm base b and exponentiation of b are function inverses of each other. So to solve something that had a log base 2 in it, what I would do is raise 2 to the power of both sides. This is essentially doing the same thing on both sides, or another kind of substitution axiom. Once I do that, this composition cancels and just leaves me the argument of 5x minus 4. On this side, I have something that I can evaluate. 2 to the third is 8. Now it's just a linear equation, which makes it pretty easy to solve. We use inverse operations to isolate my x, and that's that. Moving on. Before we can use inverse operations to cancel logarithm, we're going to have to make it so that there's a single logarithm, and that's going to involve using the properties of logarithms. Remember that a sum between logarithms can be brought inside as a product. And so we could bring these x and x minus 2 terms together in product inside of a single logarithm. Raising both sides into the power of e, we cancel on both sides to reveal if we distribute, we find we're dealing with a polynomial, and hence we apply some of our polynomial tricks in order to solve. Setting it equal to 0 and factoring, we wind up with these two solutions. However, we must be cautious. We're not allowed to plug in 0 or a negative into a logarithm. And so this solution of x equals 0 actually won't work, because that would make this logarithm undefined. So we have to test our values to see if we have any domain restrictions. But in this case, x equals 4 would work in the argument of all logarithms, and so will be one of our solutions. As such, this next one requires something similar. The only difference is now we have subtraction between logarithms. This will come inside of the logarithm as a quotient. Hence, we want to rewrite this as the log of x plus 4 divided by x plus 3 is equal to 2. This is the common log. We don't see a base. So we'll raise 10 to the power of both sides. That cancels on this side and gives me just this argument, x plus 4 over x plus 3, equal to 10 to the 2, which is 100. We want to now clear denominators by multiplying on both sides by x plus 3, which cancels on the left and gives me x plus 4 is equal to 100 times x plus 3. Distributing my 100 and grouping like terms, I can now solve for x by dividing by 99 on both sides, which gives us our answer. Notice that 296 divided by 99 is going to be something less than 3, and as such, we're going to be able to plug negative that into both of these terms without it being negative or 0. So this is a valid solution. Okay, moving on. Here we have log base 13 of both sides. This 15 on the outside can be brought inside of the logarithm as an exponent. We could then raise 13 to the power of each side to cancel our log bases 13 and give me 2x plus 4 to the power of 15 is equal to 14. Here I would then take the 15th root of both sides, which would not really reduce, and then solve this linear equation for x, which we could do by minusing 4 and dividing by 2. And as odd as that looks, this is our answer. We would want to check that this answer actually would be acceptable inside of this logarithm, which we could do either by calculating its value and then multiplying by 2 and adding 4, or simply noticing that if we multiply this by 2 and subtract 4, we're going to get precisely this value of the 15th root of 14. And say what you will about it, it's at least going to be a positive value greater than 1. If we're going to multiply a number by itself 15 times and have it get to 14, it's got to start greater than 1 so that we can make it larger by a little bit each time. At the very least, it's not going to be negative, and so this argument is going to work out just fine. Okay, moving on. The first thing we want to do here is combine our like-based logarithms by multiplying. This could be rewritten as log base 48 of x times x plus 8, and that's going to be equal to 1. We now raise 48 to the power of both sides to cancel this. 48 to the 1 is just 48. And we have that equal to distributing x squared plus 8x. Once we bring that 48 over, we can factor this equation to solve the polynomial, and what we'll wind up with is x plus 12 and x minus 4. This gives us x minus 12 and positive 4 as solutions. Let's see if either of those work. Well, we can't use negative 12 because that would put a negative into this logarithm here, but we can use 4, and so 4 will go into each logarithm and work out. So we can get rid of this 12, and only x equals 4 persists as a solution. Here again, we're going to want to start by combining these using our difference property of logarithms. This gives me log base 13 of x plus 19 over x is equal to 3. Raising both sides into the power of 13, we're going to wind up canceling here and giving me x plus 19 over x is equal to 13 to the 3. 13 to the 3 is 2197, and we can now start to take this apart and solve it. If I multiply on both sides by x, I'll clear denominators, and so we have x plus 19 is equal to 2197x. If we group our like terms by minusing this x over, we'll have 19 equals 2196, and dividing by 2196 on both sides, we get our answer. Now, this is some small positive number, but that does mean that it works inside of this logarithm and this one, so this will be our answer. So here we want to use the fact that if we can rewrite these things in terms of a common base, like, for example, this is 9 to the power of negative 2, then we can equate the exponents involved. Not much to that one, as long as we know that if I have any base raised to some power, and any other of the same base raised to another power, I can equate those powers. As we discussed, this is because the exponential function is 1 to 1. Now, for this one, however, we cannot use the same trick, because 9 isn't really a nice power of e. What we can do instead is take the natural logarithm of both sides, which gives me a number over here, and cancels my exponentiating over here. So I just get 4x is equal to the ln of 9. Dividing on both sides by 4, I get my so-called exact answer. If we wanted an approximate solution, we would plug that into a calculator and round to some appropriate number of decimal places. As such, here they want us to proceed the same way using log. So if we take the log of both sides, we could pull this 2x out using properties of logarithms, at which point we would have 2x is equal to log of 12 over log of 5. And completing this by dividing off the 2, we have log of 12 over 2 log of 5. You could bring that 2 inside to make this a 25, but however you like to present it, this is going to be your exact solution. To finish this, we could type this into the calculator, making sure to put parentheses around the bottom, and we would wind up with an approximate decimal answer. To round to 4 decimal places, that would look like this, as such. Any logarithm that we take of both sides here is going to help us free up those exponents. This could be done in terms of natural log or common log or whatever log you like. So there's really not the exact answer, but many forms of the exact answer depending on what base we used. However, they will all have the same numerical value. Here's an example of me approaching it by taking the natural logarithm of both sides. That would bring out a 2x minus 3 times ln of 3. And on this side, a 7x minus 10 times the ln of 7. If we distribute this, we'll have 2 ln 3 times x minus 3 ln 3. And on the other side, we'll have 7 ln 7 of x minus 10 ln 7. Grouping all of the terms that don't have an x in them to one side and the ones that do to the other, I'll have the following once I factor out my x. We could then divide off that term to give me for my exact answer. If I want this answer rounded to 4 decimal places, we need to type this carefully into the calculator. Let's make sure to put parentheses around our numerator and our denominator as such, and this would be our approximate answer. This next one is going to follow almost exactly the same moves. If we take the log of both sides, we're going to free up our exponents out to the front as multiplication. Distributing and then grouping like terms, we have the following. Now factoring out my x and dividing it off, we get this exact answer. Making sure to put parentheses around our numerator and denominator, we get the following answer when we type this into the calculator, which rounds as follows to 4 decimal places. For the following problem, we want to take advantage of a substitution trick. We see here that we have something which is 2 times greater in power then this other something, and then a term which has no somethings in it. This gives us an indication that we might consider making the following substitution. If we do, we wind up with u squared, because that is indeed e to the 4x squared. Power to a power is the product of powers, minus 4u minus 32 is equal to 0. This is a polynomial we can factor and get two solutions for. Now, e to the 4x is only going to have a positive value. So this second equation that says e to the 4x is equal to minus 4 has no solutions. We can stop right there. However, this one we can solve by taking the log of both sides, which gives me 4x equals to ln of 8, then dividing by 4 to give me 1/4 the ln of 8. And that is indeed my answer. We're going to want to set up the next one with the following trick. Notice that if I rewrite this as 2 to the power of 2, we have 2 to the 2x here. And this one, if I rewrite this as 2 to the 2 times 2 to the x, then we wind up with some kind of doubling pattern in the exponent. We didn't quite have that here because this is plus 2. That's not quite a doubling of what's happening here. But now that we do have that pattern, we have something that's almost a quadratic. If I make a substitution like this, then u squared is going to be equal to 2x squared, which is 2 to the 2x. And so we wind up with something now that looks like this. This is a polynomial that I can factor to give me u equals 7 and u equals minus 3 for solutions. But remember, u is actually 2 to the x. And so I can't really take this 2 to the x and have that be equal to minus 3. 2 to the x is never negative. So this isn't really a solution set. On the other hand, on this side, I can take the log base 2 of both sides to give me a solution. Alrighty, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.